A typical condensate and feed water system has several shell and tube heat exchangers or closed heaters. Some may be used as condensers, but most are used as low, intermediate, or high-pressure heaters for the condensate and feed water. The levels, temperatures, and pressures for all the closed heaters should be checked periodically during normal system operation to make sure that these operating variables remain within predetermined normal ranges. We'll look at some operating checks for a high-pressure closed feed water heater. Most of the checks for this type of heater also apply to low and intermediate pressure condensate or feed water heaters. To monitor the level in the shell side of the heater, you can usually check a sight glass on the heater. An abnormal level in the sight glass could indicate a problem that should be reported. Temperature gauges indicate the temperature of the feed water leaving the heater and the temperature of the extraction steam entering the heater. For proper system performance and the overall efficiency of the plant, it's very important that these temperatures stay within their normal operating ranges. Pressure gauges are used to monitor the pressure of the extraction steam that enters the heater and the feed water that passes through the heater. The reading for the extraction steam pressure normally varies with turbine load. The greater the turbine load, the higher the extraction steam pressure. Feed water heaters in many condensate and feed water systems are installed in trains or strings that are monitored as a unit during normal operation of the system. In this arrangement, the final feed water outlet temperature is commonly used as one way to monitor the performance of the heaters. The final feed water outlet temperature is the temperature of the feed water coming out of the highest pressure feed water heater on its way to the boiler's economizer. Checking this temperature is the quickest way to get an overall picture of how well the feed water heaters are doing their job. If the final feed water outlet temperature is at the expected level for the given load, then each of the feed water heaters in the train is probably transferring heat at the proper rate. But sometimes a heater within the train may be transferring heat at an improper rate, even though the final feed water outlet temperature is at the expected level. So periodically, you should also check the outlet temperature of each heater in the train. The deaerator, which is an open heater, and the hot surge or deaerator storage tank that's associated with the deaerator must also be monitored when a condensate and feed water system is in operation. Check the level of water in the hot surge tank. There's usually a level sight glass on the tank that's used for this purpose. If the level is too high, water could flow into the deaerator and, in extreme cases, even into the extraction system piping. If the level is too low, the net positive suction head for the pumps downstream of the tank is reduced. As a result, the pumps could be damaged. Monitoring the performance of the deaerator is important for maintaining overall system and plant efficiency. Check the appropriate gauges for the proper extraction steam temperature and pressure. Look for any signs of leakage and make sure that all the valves for the deaerator are in the proper positions. Watch for excess venting from the deaerator. That can cause a major loss of heat energy and fluid from the deaerator, which will decrease plant efficiency. Also watch for insufficient venting. That will allow oxygen and other gases to remain in the condensate and feed water system and cause problems downstream. Problems can occur with any of the components in a condensate and feed water system, including the pumps, heaters, storage tanks, and their auxiliaries, such as valves, vents, motors, couplings, and piping. In this part, we'll look at typical examples of dealing with some operating problems that are common in most condensate and feed water systems. But keep in mind that you'll need to review your plant's standard operating procedures to learn the exact steps to follow in your facility. Many operating problems in a condensate and feedwater system are relatively simple to correct. However, a problem in one component usually affects the operation of other components in the system as well. Consequently, some operating problems can require considerable troubleshooting skills. Several heaters are included in a condensate and feedwater system, so heater problems are a typical operating concern. We'll look at some problems in a closed, high-pressure feedwater heater. Improper venting of a heater can cause air binding. When this occurs, air is trapped in either the tube side or the shell side of the heater. Air that collects in the water boxes on the tube side of the heater can restrict the flow of water through some of the tubes. The restricted flow causes the velocity of the feedwater to increase because the same amount of water must go through fewer tubes. The increased feedwater velocity can cause the terminal temperature difference, or TTD, to increase, although the drain cooler approach, or DCA, remains normal. Another indication of air binding in the water boxes is an increase in the differential pressure, or delta P, across the heater. If air binding is indicated by either an increased TTD or an increased delta P, venting the air from the water boxes should return the feedwater flow and pressure to normal. Air binding also occurs if air and gases collect on the shell side of the heater. The increasing volume of air blankets the tubes and prevents steam from contacting them. This, in turn, reduces the amount of heat transferred by the heater. As a result, the feedwater outlet temperature decreases. The TTD, however, increases because the extraction steam temperature remains the same, even though the feedwater outlet temperature has gone down. The efficiency of the drain cooler isn't affected, so the DCA remains normal. You can usually correct the problem of air binding on the shell side of a heater by venting the shell side to remove the air. The TTD should then return to normal. As a result of the restricted heat transfer caused by a high heater level, the TTD increases. The DCA, however, usually remains normal because the flow of drips through the drain cooler may not change, or it may be less than normal. To determine whether an increased TTD is caused by air binding or by a high level, check the sight glass for the shell side of the heater. If the level in the sight glass is high, then the problem is most likely caused by an abnormal level, not by air binding. If a heater's level is too low, steam is able to blow through the heater and out the drain. In turn, the flow of extraction steam increases, and this can cause erosion inside the heater and eventually tube failure. Because the low level allows steam to flow through the heater's drain cooler without condensing, a low level causes the DCA to increase drastically, while the TTD typically remains at or near normal. Tube leaks are another common operating problem associated with closed heaters like this high-pressure feedwater heater. Even small leaks can significantly increase the volume of water in the drips, causing the lower tubes in the heater to be blanketed with feedwater. Tube leaks also make the heater's level control valve open farther than normal. As a tube leak becomes larger, the volume of water flowing into the shell side of the heater can exceed the level control valve's capacity. Then the emergency drain valve must be used to control the level in the heater. A large tube leak is a serious problem that calls for immediate attention because it can allow water to enter the turbine. To prevent damaging or destroying the turbine, you should isolate and bypass the heater as soon as possible. Of course, operating with even a relatively small tube leak is inefficient, so it's important to find small leaks early and get them corrected. Small tube leaks may be difficult to detect, though, because they don't show up on instrumentation. but some small leaks may become noticeable when you calculate the TTD and the DCA for a heater. In many cases, operators must determine exactly which heater in a train is not operating properly. In this example, one heater in a train of high-pressure feedwater heaters is malfunctioning. As a result, there's an increase in the temperature difference, or delta T, across the higher pressure heaters downstream from the malfunctioning one. The increased delta T causes more heat to be transferred in the downstream heaters, making up some of the difference caused by the heater that's not operating properly. To locate the heater that's not operating properly, you should generally start by checking the final feedwater outlet temperature to see if that value is within the normal range. Then work backwards, noting the heater outlet temperature for each heater in the train. If the difference between the actual reading and the expected one becomes greater with each heater, there's a malfunctioning heater upstream. To pinpoint the exact heater that's causing the problem, follow a step-by-step troubleshooting procedure, which includes checking the temperature rise across each heater, calculating their TTDs and DCAs, and checking the positions of their normal drain valves. Then comparing the actual conditions with the expected normal conditions for the heaters at the given load. A typical condensate and feedwater system also has several pumps, so operating problems often involve troubleshooting pump malfunctions. For example, this operator notices that although this boiler feed pump is operating at top speed, the flow of feed water to the boiler is inadequate. To keep the situation from getting worse, a second boiler feed pump is brought online. This increases the feed water flow to an adequate rate to keep the boiler operating properly. Then company procedures are followed to analyze and correct the problem. Detailed troubleshooting could determine that the inadequate feed water flow was caused by an operating problem in the first boiler feed pump. On the other hand, further analysis could show that the pump is working properly, and a malfunction elsewhere in the condensate and feedwater system could be the cause of the inadequate feedwater flow.